In this short video clip, I'm going to explain how to assign priority to atoms and groups according to Cahn-Ingold-Prelog rules. This system of assigning priority to atoms and groups in organic chemistry is important because this helps us to assign configuration in geometrical isomers and optical isomers. So, the rule is, according to Cahn-Ingold-Prelog, the atom of greater atomic number or atomic mass has got higher priority. So when we think about all the elements which are usually present in organic compounds, these elements, the common ones are carbon, all the halogens, iodine, bromine, chlorine, fluorine. Then you have oxygen, nitrogen, sulfur and phosphorus. These are the most common elements, and of course hydrogen is there, which are found in organic compounds. Now when you consider the atomic number or atomic mass of these elements, we can list them from biggest to smallest as follows. So iodine has got the highest atomic number. So iodine has got higher priority than bromine, and then chlorine, and then sulfur, and then phosphorus. Then we come to fluorine, then we come to oxygen, greater than nitrogen, greater than carbon, greater than hydrogen. So this will be the order of priority according to Cahn-Ingold-Prelog rule. Now how can we use them when we are doing configuration of geometrical isomers or optical isomers? In geometrical isomers, as you know, we have alkenes or double bonded compounds, and then the attached groups to these double bonded carbons have to be assigned priority before we can assign the configuration. So in this case, suppose I'm having 4 different atoms attached to these 2 carbons. I'm having I here, and then maybe fluorine here, then bromine here and chlorine here. How do we assign configuration based on the priority? So we have to look at the 2 atoms attached to each of the sp2 carbon separately. So let me just number this carbon as 1 and 2. So the 2 atoms attached to the carbon 1 of the alkene are iodine and fluorine, and according to the CIP rule priority, iodine is having higher priority, so this will be high and this will be low. Now we will look at the other carbon numbered 2 and the 2 atoms attached to that carbon. So in this case, bromine is of higher priority, so we can put this as high, and chlorine, which is having lesser atomic number, is having lower priority. Then we compare the positions of the high priority groups. If the high priority groups on the carbons 1 and 2 are on the same side of the double bond, we give the configuration as Z. If they are on opposite sides, for example, if I have the compound like this with iodine here and bromine here and chlorine here and fluorine here, then of course the positioning of the priority will be, this is low and this is low, this is high and this is high. In this case, the 2 higher priority atoms are on the opposite sides of the double bond, and hence the configuration in this case, it will be E. So this is how you make use of the priority to assign configuration to geometrical isomers. In a similar way, we can use the same rules for assigning priority to groups or atoms on a chiral carbon and assign R or S configuration to the chiral carbon as follows. So if you have a chiral carbon here, let us say this C is a chiral carbon, which means 4 different atoms or groups are attached to this carbon. So I'm going to put a hydrogen here, a chlorine here, a fluorine here, and some other group. Let us put it as bromine, okay? So then here we assign the priority like this. Out of the 4 atoms attached to the chiral carbon, the highest priority one is bromine, so we will put 1 here. Next is chlorine, so 2 here. Next is fluorine, so 3 here. And next is hydrogen, so 4. When we look at we ignore the lowest priority group, which is hydrogen. We don't look at it. And then we move our finger from the atom or group of priority 1 through priority 2 to priority 3. If this movement is clockwise, we give the configuration as R, and if this movement is anti-clockwise, we give the configuration as S. In this particular case, the movement of my finger from atom of priority 1 to 2 to 3 is anti-clockwise, and so the configuration of this molecule will be S. So this is how we make use of Cahn-Ingold-Prelog rule to assign priority to atoms and use that priority to assign configuration to geometrical isomers or optical isomers. Now these 2 examples are very simple because we have just used only 1 atom for each of the substituents. Suppose we have groups of atoms like in the functional group OH, NH2, COOH, etc. Then we have to see how to assign the configuration to these groups. This is done as follows. So suppose I have the group suppose I have the alkene C double bond C, which is attached to the group OH, and then here it is hydrogen, and here I have a CH3, and here I have a CH2 CH3. In this case, it is a little bit more difficult to assign the priority and hence the configuration because it is not a single atom which is attached to these bonds. OH is a group, CH3 is a group, CH2, CH3 is a group, and they are all different also. So in this case, in order to assign priority to groups, we only have to consider the atom which is directly attached to the double bonded carbon. We cannot consider the whole group together. We have to consider it as only the atom directly attached. So in this case, oxygen is the atom directly attached and hydrogen is the atom directly attached. And we have to look at the atomic numbers of these 2. Oxygen is higher, greater, so hydrogen will be lower and oxygen will be higher. So this will be high and this will be low. On the other side, we have CH3 and CH2 CH3. Now, that is a little bit more confusing because the atom directly attached to the sp2 carbon or the double bonded carbon are both identical. They are both carbon. So then we cannot differentiate between them as high and low. In these cases, what we have to do is we have to go to the next atom which is attached to this particular carbon. So in this case, we have on the carbon on top, we have 3 hydrogens. Let me just write them separately so that you can see it clearly. So these hydrogens directly attached, and on the lower alkyl group, the atoms which are directly attached to that green carbon are 2 hydrogens and a carbon. So in this case, we will be having 2 hydrogens and a carbon. And then that carbon, of course, is again attached to 3 other hydrogens. Alright. Now here when we go to the second level, that is the blue colored ones. So here we have 3 hydrogens and here we have 2 hydrogens and a carbon. So these two are identical to these two. We cannot compare them. But when you consider this hydrogen and this carbon, they are having different atomic numbers. Carbon is greater than hydrogen, and so therefore this group will be high and this will be low. Thus, this alkene configuration is having 2 higher priority groups on opposite sides of the double bond, and so the configuration will be E. Whenever you are writing the IUPAC name of an alkene with 4 different groups or 3 different groups, you have to write this configuration E or Z before you write the name of the molecule. So in this case it will be E, and this molecule is, of course, it's a butene, butanol, with a methyl group at position 2. So we will be calling it as 2-methyl but 2 but 1 ene 1 ol. This will be the total IUPAC name of this compound. But most important here is how to assign the configuration, or how we have assigned the configuration when we are having these 2 different groups which are having identical atoms attached to the double bonded carbon. So then we go to the next level. Now in this way we must be able to assign priority to any groups in order to assign configuration to alkenes or chiral carbons. So in another video we will see the priority of various different groups. We will see how to assign the priority to various different groups.